Order of magnitude. An order of magnitude is the power of 10 that is closest to the actual value of the quantity. Estimators use orders of magnitude all the time when they're doing estimating in terms of land and carpeting and square footage. They'll come up with a number that is a quick order of magnitude that gives them a ballpark figure for doing an estimate. For example, the mass of a person is 75 kilograms. Well, you could do orders of magnitude on that and say, well, that's approximately 10 squared kilograms. So the person's mass is on the order of 10 squared, 100 kilograms, reliable to within a factor of 10, because 100 is just a little larger than 75, so you're in the ballpark. 10 cubed is 1,000 and is a value of 3 orders of magnitude. So you can take a look at a value and determine using a factor of 10 what the ballpark figure would be. This is a cute example. McDonald's sells about 250 million packages of French fries every year. If these fries were placed end to end, how far would they reach? Well, we can make an assumption here that the average length of a French fry is about 3 inches. I always look for the long ones myself. The average number of fries in a package is approximately 30 per package, or 3 times 10 fries per package. So, if 3 times 10 fries per package times 2.5 times 10 to the 8th packages sold every year at 3 inches per fry, we end up with a figure of 2.2 times 10 to the 10th inches as our approximation. 2 times 10 to the 10th inches. So if we convert our inches to meters, 2 times 10 to the 10th inches is equal to 2 times 10 to the 10th times 1 meter per 3.937 times 10 to the inches. Okay, so that's our conversion. 1 meter per 3.9. So if we wanted to do an approximation on that, we would say, okay, well, 3.937 is approximately 4 times 10 inches for that same 2 times 10 to the 10th, and we would have approximately 5 times 10 to the 8th meters in length for all of those French fries. Now, we go to our table and look up the distance from the Earth to the Moon, and it ends up being about 4 times 10 to the 8th meters. So, within a factor of 10, 5 times 10 to the 7th meters to 5 times 10 to the 9th meters would end up being our total distance. It's helpful to know and to review mathematical notation. Mathematical notation are all of those values or those symbols that end up being operators and or in this case equality signs and other signs that help us annotate and shortcut when we're doing mathematical notations. So the equal sign, the not equal sign, the approximately equal sign, all values you're probably well familiar with. Proportionality, something you probably haven't used as much. Using 3 lines instead of 2 lines is defined as your less than, greater than, less than or equal to, greater than or equal to, much less and much greater than signs are all values or symbols that you probably used in the past. And then the last 2, the delta notation and the sigma notation, identifying delta as a change and sigma as a summation. So these are all notation that you should be familiar with when you're doing a lot of math in a class like physics. The delta notation, in this case delta x, indicates a change in the quantity x. So in the expression, delta x, or the change in the quantity x, is defined as x final minus x initial position. So we're looking at that change over a distance. The sigma notation, the Greek capital letter sigma, indicates a summation. So if we have many terms that we're adding together, instead of saying x plus x plus x plus x plus x 5 times, we can say sigma 5 over the top, where the initial position, the initial value is 1, sum all the values of x sub I. The magnitude, or absolute value, then, is something that becomes very important, especially in doing labs. When you're doing your labs, the significant errors, difference in percentage of errors and percentage of difference end up being values in the expression where you will use the absolute value. We use the absolute value because we don't want a negative number. We're not going to use a negative number when we're going to associate a value with a percentage. Coordinate systems. You're probably very familiar with the rectangular or the Cartesian coordinate system, as shown on the bottom of the page here. Many aspects of physics deals with, in some way, the locations in space. So in a two-dimensional space, x and y, you will end up with 2 coordinates per set of identifying points on that coordinate system. We need a method of describing the position of a point in space. 1 coordinate defines a point on a line, 2 coordinates define a point on a plane, and 3 coordinates define a point in space. So looking at terms associated with coordinate systems, the x-axis being the abscissa, the y-axis being the ordinate, and then each of your pairs of coordinates are shown. xy, p53, q minus 35, and then, of course, the origin. Another system that you will become familiar with as we get into vectors more is the polar coordinate system. The polar coordinate system uses a radius from the origin and an angle that it makes from the horizontal, or the x-axis. A point is specified by the distance r from the origin to the point, and an angle theta between a line from the origin to the point and the reference line, typically the axis. The angle theta is considered positive when it's measured counterclockwise from the reference, and negative when measured clockwise. Another area that you'll become familiar with as we do vectors is the trigonometric functions of a right triangle. And in understanding sides and angles, first thing we need to look at with a right triangle, you'll notice that a right triangle has one angle that is 90 degrees. And the 3 sides that make up that triangle become the side opposite, A, the side adjacent, B, and the hypotenuse. The opposite relates to the angle theta. So if you look at the angle theta being made on the lower left-hand corner, the side that's opposite that angle is A. The side that's adjacent to that angle is side B. And then the distance between the 2 points, the farthest reach on the opposite and adjacent, becomes the hypotenuse, or side C. An easy way to remember the relationships between sine, cosine, and tangent is the use of the sides of the angles. The sine of the angle theta is the side opposite and the hypotenuse. So A over C, and it can be abbreviated SOH or side opposite hypotenuse. The cosine of theta is the sine adjacent to theta divided by the hypotenuse, which is side B or C, and we call it the cosine adjacent hypotenuse. So, ca, the last one, toa. The tangent theta is the side opposite the angle theta and the side adjacent angle theta, or A over B. So SOHCAHTOA, quick mnemonic to remember what sine, cosine, and tangent is as it relates to the sides of a right triangle. The basic trigonometric functions defined by a right triangle are the ratios of the lengths of the sides of the triangle. The quantities are without units. Each represents the ratio of the two lengths. And since it's a ratio, if you had units on there, they would cancel out anyway. Another mathematical expression you'll use, mostly algebraic, is the Pythagorean theorem. The Pythagorean theorem states that the relationship exists between the lengths of the sides of a right triangle. In that relationship, stated mathematically, is the hypotenuse, c squared, is equal to the opposite, a squared, plus the adjacent, b squared. Or the hypotenuse is equal to a squared, the square root of a squared plus b squared. We also have to get used to something called an inverse relationship. An inverse relationship is what angle has a sine of 0.866. Okay, so you're looking at, instead of solving for the relationship itself, the sine, you're asking for the angle that is made up by doing the calculation of the sine. So in this case, the notation is sine with a -1 like an exponent, and then that sine value, 8.66. So what angle has a sine of 8.66? Okay, and then if we did the inverse sine, we would get an angle for theta. The next thing that's very important is problem-solving strategy. In every technical class, you are going to be given problems, and from those problems, as a written problem, you're going to have to assemble them into a mathematical solution that you will have to glean from the way the problem is stated. So in every case, the first step is reading the problem carefully. Read it through a couple of times. Be sure that you understand the nature of the problem before proceeding farther. So at this point, you're going to start looking at the problem, reading through it, and trying to determine what you know and what you don't know, and start identifying and gathering the knowns and determining what you have to do for the unknowns. If you can, draw a suitable diagram with appropriate labels and coordinate axes. This becomes very important, especially as we start doing vector diagrams and some of the force diagrams, where you can draw a diagram and it will allow you to label the forces and the lengths on that diagram. And then as you're reading it, try to imagine it as a movie running in your mind of what happens in the problem. So think about what activity or action is going on. The fourth step then is, as you examine what's being asked of the problem, identify the basic physical principle or principles that are involved, listing the knowns and the unknowns. So as we go through problems here, you're first going to be solving for motion, velocity, acceleration. Identify those types of physical aspects. And then as we move into force, you're going to start identifying what things can be calculated from velocity and acceleration and length to determine force. And then as we get into energy, we'll start adding more units like time and derive values from force. So it ends up being a pathway of physical principles that allow you to solve for the unknowns. Step 5, select a basic relationship or derive an equation that can be used to find the unknown, and symbolically solve the equation for the unknown. This is where keeping a notebook handy with all of the all of the equations that you've encountered during your studies. Whenever you encounter a new equation, a new relationship, a new representation or manipulation of an equation, write it down and make some notes about how it's used in a specific situation. It will help you navigate through tricky questions as you go through chapter by chapter. Step 6, substitute the given values with the appropriate units into the equation. So you have to be very careful. It's very easy to confuse velocity and acceleration. And if you do and you don't have your units correct, you're going to end up with the wrong answer. The other thing is check your factoring and your unit analysis, as we did with the L's and the T's earlier. Obtain a numerical value with units for the unknowns. You can have confidence in your result in the following questions if they're properly answered. A, do the units match? That comes down to, does it make any sense? Does the number make any sense? Do the units make any sense for what you are looking for? If you come up with velocity and you know that the answer should be acceleration, you know that the problem doesn't make any sense. Is the answer reasonable? Is it too big? Is it too small? Did you expect a big number or a large number? And if that's not what you got, then you've got a problem. And then look at the polarity. Is this plus or minus sign proper and meaningful for the answer that you just calculated? So if you look at it diagrammatically, a guide to problem solving, then you can see step by step. Read the problem, draw a diagram, identify the data, choose equations, solve the equations, evaluate, and check your answer. So if we look at an example here, read the problem carefully at least twice. Be sure to understand the nature of the problem before you proceed. Problem statement. An airplane travels 450 kilometers due east, travels an unknown distance due north. Finally, it returns to its starting point by traveling a distance 525 kilometers. How far did the airplane travel in the northerly direction? So you're going to read through that the first time, get an idea, get a picture, a scope, and then you're going to read through it again and start thinking about how you're going to assemble and solve this problem. Then the second step said draw the suitable diagram. So you can create a quick right triangle here and put in the values labeled as the sides of the triangle, determine which values you have, which one you don't have. Since it's asking for the northerly direction, we know that side B is going to be what we're solving for, the northerly direction. And then go back and think about this like you're running a movie in your mind as you reread the statement and look at your diagram and start doing an image in your mind of what you think is going on in the problem. As you examine what's being asked of the problem, then identify the basic physical principle or principles that are involved, listing the knowns and the unknowns. Since we know in this problem that a given was that the airplane travels 450 kilometers due east, we can mark that down and attach it to our diagram. It returns to its starting point by traveling 525 kilometers. Okay, so you can start adding these to your diagram. The hypotenuse C and the side A adjacent then are the two known quantities associated with those values. Step 5, select a basic relationship or derive an equation that can be used to find the unknown and symbolically solve the equation for the unknown. So in this case, since we're using a right triangle, it makes sense that maybe we should start with the Pythagorean theorem because it relates to three sides of a triangle and how each side relates to the others. So you can start with the basic relationship, c squared equals a squared plus b squared, and start moving terms around because we know that what we're really looking for is side B. So you start doing the mathematical algebraic manipulations of moving terms from one side to the other by subtracting or adding until you get the one term you're looking for, B, or in this case, it's B squared, by itself. Now we start using some of the special properties, in this case of squaring and taking the square root. If I take the square root of a squared number, I end up with that number on the left side. On the right side, I end up with the difference in C squared and A squared as a square root. So now once I get it to that point, I'm ready to start inserting my values into the equation. So C is 525, A is 450. Insert them under the radical, take the squares of each of them, take the difference, and I end up with a value of B, the northerly direction, 270 kilometers. Now, the next thing to do is take a look at that number and think about, does that make sense? Is that unit, that answer justifiable? So ask yourself, do the units match? In this case, kilometers, they match. Does the answer seem reasonable? The answer seems reasonable based on the lengths of the two sides of the triangle. And do I have a plus or a minus sign? In this case, I do not. So I've gone through the process of solving a problem methodically to determine whether or not I think I have a good value in the end. Okay, so we've looked at these areas: measures, units, metrics, analysis, conversions, significant figures, and problem solving in this whole first section. So the next section then we will look at, the next chapter, will deal with velocity, speed, acceleration, and objects in motion.